Hi, welcome to my Physics 2211 Lab 4, and let's get started. So, the introduction. The purpose of this lab was to compare the predicted motion from GlowScript with the observed motion from Tracker for a mass spring system that's oscillating. The goal was to determine whether the model followed the energy principle. So, the key concepts that we needed to understand was Newton's second law, which is the system's change in momentum proportional to the net force applied, which we can see here. This is the force of the spring and the force of gravity, and we can see that over here. And the energy principle, which is the system's change in energy, is the sum of the work done by the surroundings and the thermal energy exchanged with the surroundings. So here's our system and our surroundings, and Q, which is the energy exchanged. And here's the system, and it's the mass spring in the earth. And that's what I said here, mass of open earth. And the surroundings is nothing. I just wrote it a little easier up here so you can see. And the change in E system is 0. So the change in kinetic energy, the change in potential energy of the spring, and the change in potential energy of gravity. Okay, so here's the preview of the results. This is my tracker, and this is my computational results. So the observed motion, the object's mass was 0.402 kilograms. The stretch length of the spring was 0.70 meters. The initial position with my tracker calculations was 0.11 or negative 0.113 and negative 0.738 meters in like that vector. The initial velocity was 0 meters per second, and I calculated the spring constant to be 6.83 newtons per meter by solving for the period and then solving for the spring constant. And then I solved for the relaxed length of the spring, which is 0.123 meters. So here's my computational model, and here's all those initial values that I got previously that I put into the computational model to get it to work. And then here is where I edited the lines to get the length and the L hat and S to make sure that everything would work properly in my code. Then the kinetic energy, the spring potential energy, the gravity potential energy, and the total energy, which is just all of those combined. And here again is the long version of the computational model. We have the force of gravity, the force of the spring, F net, which is both of those. We have the velocity update formula, the position update formula. We're updating the spring then too, and we have spring axis, which I didn't have to change. I just had to change these three. And then we're calculating the energy changes. So delta K, which is the change in kinetic energy, and gravitational potential energy and the change of gravitational potential energy, and that keeps going. So you get that from there. And so here's what it looked like. And the errors that I can conclude from this is that the system isn't really isolated in reality like it is from the code. So there will be work done in the surroundings. There was inaccurate clicking by my part on Tracker, and that there were rounding errors. So with all of this, like I may have also needed to place the axis in a different location on Tracker because that's why my Y values might have always been negative. That's probably the error on my part. And for the questions, for your model system, is the energy principle satisfied? I said yes, since there are no external forces acting on the isolated system, the change in energy is 0. And the graph corroborates this by showing the total change in energy is constantly and consistently 0. So you can see that the red and the green even out, and they get to delta E, and delta E is 0. And then using the data I obtained from Tracker, I made two separate estimates of the oscillation periods. And so this is for the X oscillation period, it's 1.614 seconds. And for Y, it's 1.804 seconds. So it might have just been that where I was clicking on the mass, it took a longer time for it to go back up on the Y position than it did for it to get across on the X position. And that is my whole lab.